Okay, in this video we're going to look at unsigned numbers. These are integers, so whole numbers, but they are only positive. So no negative numbers. When we're storing data in the computer, it's really important to distinguish between the different types of numbers. Okay, because we can store decimal numbers, floating point numbers, signed numbers, unsigned numbers, signed numbers of different lengths, etc., and they all need processing differently. So when we're actually thinking of the internal storage in binary of these things, we have to actually look at it in a more complex way than just it's a number. Okay, so we're going to look at unsigned integers to start with. So let's have some bits. Okay, so I'm going to look at 4-bit number to start with. So I'm going to start by drawing some column headings. So start at 1 and then just keep doubling up. So 1, 2, 4, 8. So this will allow me to represent an unsigned number. Not a very big one, but it'll let me represent. Okay, so the smallest number would be if we set all the bit values to 0. So that would be the number 0. Okay, so we've got no 8s, no 4s, no 2s, and no 1s. The largest number will be if we set all the bits to 1. Okay, and to compute what that number represents, we just add up wherever we've got a 1. So we've got an 8 and a 4, which is 12, plus a 2, which is 14, plus a 1, which is 15. So with 4 bits, the smallest number we can represent is a 0, and the largest number is a 15. Now there is a mathematical way of representing this. You can say that the largest number is 2 to the power n minus 1. Okay, which is a bit of a mouthful. So 2 to the power n. So in this case we've got 4. These are n, 4 bits. So we say 2 to the power 4, that's 16 minus 1. Oh yeah, that's 15. But there's an incredibly easy, quick way of doing it. It's also the same as the next column minus 1. So the next column along would be 16, and we just make the next columns by doubling up. So you don't have to remember this formula. You can just say, oh, it's 1 less than the next column. Because it would be. Because if we had 5 bits, the number that is 1 bigger than 15 would be that. Okay. So 15 is a 1 less, and that's what, if I was to subtract 1, that's what it would look like in binary. Okay. So you can say 2n minus 1, or you can say value of next column minus 1. And that's the easier one to remember. Okay, so one of the sort of questions you'll get asked is say, right, well, how many bits do we need to represent this number? So they'll give you a number like 294, and they'll say, right, how many bits do we need? So you need to be able to calculate this to determine whether a certain number of bits is going to be enough to hold the largest value. So let's say we was going to try and represent 297. Okay, so we'd start off and we'd say, right, okay, so obviously it's not going to be 4 bits. Right, 16. Now the next column is 32. Okay, the next column will be 64, which would allow us to, and what I'll do is in another color, I'll just put those on. So with 1 bit, okay, the maximum value is going to be 1 because it's 1 less than the column to the right. So this one, with 2 bits, the maximum value, remember 0 is a value, so we've got 0, 1, 2, 3. With 4 bits, it's going to be 1 less than that, the maximum number. So this is the maximum. And we're desperately trying to get to 297. Let me just move 297 out of the way. It's going to be in the way there. Right, so we're going for how many bits for 297? So let's just carry this little bit on. So for 8, it's going to be 1 less than that. So that's going to be 15, which we've just talked about. For 5 bits, it's going to be 1 less than this. So that's going to be 31. So we can represent 31. For this one, we need to know what the next column is. So that's 64. So that means that's going to be 63. So with 1, 2, 3, 4, 5, 6 bits, we can represent the numbers 0 to 63. Okay, let's keep going. So that's not enough to represent 297. So the next column, 64, after that it would be 128. So with 7 bits, we can represent 128 minus 1, which is 127. Now, when you do a lot of binary, you'll just remember all these numbers anyway. Okay, so 7 bits isn't enough. What about 8 bits? So the next column would be 256. Now we can see that 256 is less than that. So we can represent the largest number in 1 byte or 8 bits would be 255. Okay, so 8 bits isn't going to be enough. Let's see what the column after 256 would be and see if 9 bits is enough. So 256, double that up, you get 512. That's looking promising. So with 9 bits, we would be able to go up to the number 511. So we could use 9 bits to be able to represent a maximum value of 297. So that would require 9 bits. Okay, so the only problem with unsigned numbers is you can't represent negatives. Okay, and it makes also arithmetic hard. And the fact that actually, if you did a calculation and it ended up negative, so like taking 5 away from 4, you wouldn't be able to represent the -1. Okay, so in the next video, I'm going to show you how to represent signed numbers, but there is a caveat with that. There are a couple of different methods. So let's just have a recap of what we've got here. So unsigned numbers start at 0 and they go up to the maximum value. And if you ever wanted to find out the maximum value, you could just write down all the ones. So in this 9-bit value we've got here, and you just add them all up where you've got a 1. Okay, but I showed you a little quick calculation. It is just write down what the next column is, and it's 1 less than it. So all these added up together, 256 plus 128 plus 64 plus 32 plus 16 plus 8 plus 4 plus 2 plus 1 adds up to 511. Okay, in the exam, you're not allowed to calculate it, so it's no good being able to do these formulas and remembering these complicated formulas. You need quick, simple methods, and this is a quick, simple method for storing. If you want to read a number that's written in binary, so let's say I've got a 6-bit number, so I'm going to write column headings down for 6 bits. And if I was given this number, all I would do is I would say that's 32 plus 4 plus 2, okay, which gives me 38. So as an unsigned 6-bit value, this number in denary is 38. They're the same number, they're just written in different number bases. Base 2, base 10. Okay. Really, that is all there is to say about unsigned numbers. So in general use, we use nibbles, 4 bits. We'll use 8 bits, a byte. We'll use 16 bits. We'll use 32 bits and 64 bits. Depending on what sort of computer you're using, in general, integers are stored in the base data bus width, which we'll talk about when we talk about CPUs. But in a 64-bit machine, when you store a number, an integer number, you're going to use 64 bits in general. Even if you're only storing the number 5, you're still going to use 64 bits. That's just the nature of how the computers work in general. Okay, so that's unsigned numbers. So the next video is going to talk about signed numbers.